What's going on, smart people? I am sure you've all had the question at some point in your lives why you can't travel faster than the speed of light. And whether it be from a friend or a colleague or maybe even a teacher, an answer you've probably read is, I can't travel faster than the speed of light because as my velocity increases, my mass also increases, which requires more and more energy to accelerate me, eventually requiring an infinite amount of energy. Today we're going to be determining whether or not that is a correct answer, more specifically whether or not your mass depends on velocity. For the most part, this video is going to be self-contained, but once we get to the actual relativistic calculations, I will be using natural units, which is where we set the speed of light, c, equal to 1. If you haven't seen that before or you're uncomfortable with it, I have an entire video linked in the description where I explain how and why you can do that. If you don't feel like watching it, just keep those factors of c in the back of your mind. Eventually, for what we're doing, those factors of c will cancel, and I won't have written them in the first place, so we'll get the same thing, which is nice. Before we can determine whether or not mass depends on velocity, or equivalently, if mass depends on your reference frame, we need to agree upon a set of criteria that will decide for us whether or not it does. And to do that, we're not going to get into special relativity yet. We're going to spend some time going over vectors and scalars, but in a way that's probably different from how they were introduced to you. So if we just want to write some vector in some coordinate system, so this is our coordinate system, x and y, and here is our vector v, we can describe this vector as a combination of x's and y's times their unit vectors in the x and y direction, right? We'll have some v is equal to some x times the x unit vector plus y times the y unit vector, and that will give us this guy. But there's no reason necessarily that we had to use this coordinate system to begin with. If we rotated our coordinate system, that's an equally valid way of describing the vector, right? So if instead of using x and y, we were to use some x prime and some y prime, where this is just saying we've taken our coordinate system and rotated it by some angle theta. So we would have in our primed frame, in our primed coordinate system, v would be some x prime times our new unit vector, x prime, plus y prime times our new y unit vector, y prime hat. And there's a relationship between the x prime, y primes, and the x's and y's. There should be, because they're equally valid ways of describing the same object. And the relationship is x prime is equal to x cosine theta plus y sine theta, and y prime is equal to minus x sine theta plus y cosine theta. Let's take a second to make sure that this makes sense. So if we didn't rotate it at all, then x prime should just be equal to x, right? And not rotating it at all corresponds to theta equal to 0. So if theta is equal to 0, this term is 0, and we just have x prime is equal to x. That's nice. If we rotate it by 90 degrees, well then our x prime should just be equal to our y. So cosine of 90 degrees is 0, and then we get sine of 90 degrees would give us y here. So we would get x prime equals y. So that's nice, and for the y prime, if we don't rotate it at all, we get that y prime is equal to y. If we rotate it by 90 degrees, we get that y prime is equal to minus x, because we're rotating it over here. So it works out. The important thing here is that it doesn't matter what weird angle you chose to define your coordinate system with. If I just use x and y, whatever it is, I automatically know how my vector is related to yours, or rather how the components of my vector are related to yours. They're related this way. And that's actually another way of defining what a vector is, not by just something that has a magnitude and a direction, but by something that has a prescription for how its components transform if I go to a different coordinate system or a different basis. So the fact that mine has that prescription, I say that this is a vector under rotations. I hope that's not too crazy so far. So vector components do change, but we know how they do. And that makes sense. If I were to shine the flashlight on this marker, the length of the shadow that I'm projecting onto the surface depends on the orientation of the surface, right? If I have a flat surface versus one at an angle or one that's possibly curved, I'll get different lengths of the shadow. But what about the length of the vector itself? Well, that's just using Pythagorean theorem. In the unprimed frame, I can take the magnitude of the vector is equal to the square root of the components in the x and y direction squared. The sum of the squares is x squared plus y squared. I don't like writing square roots, so I'm just going to define the square of the magnitude, or the square of the length, is equal to x squared plus y squared. It's just nicer to write a 2 than a square root every single time. Now, what about in the primed frame? Well, in the primed frame, we have the magnitude squared is equal to x prime squared plus y prime squared. And we have our relationship to how x prime is related to x and y and so on. So let's go ahead and substitute that in. So this is equal to, for the x prime squared, let's just square this guy. X squared cosine squared theta plus y squared sine squared theta plus 2xy cosine theta sine theta. And then the y term. So we have this guy here. So this is x, oh no, not equals, I want a plus. Is equal to x squared sine squared theta. I said equals again, I mean plus. Plus y squared cosine squared theta minus, because there's that relative minus sign, 2xy cosine theta sine theta. These two guys cancel. And we can factor out an x squared here, which gives us cosine squared plus sine squared, which is 1. We can also factor out a y squared here, which is cosine squared plus sine squared, which is 1. So that tells us that the squared magnitude, the squared length, is equal to x squared plus y squared. So that's interesting. So that means that the length of the vector, or the magnitude of the vector, doesn't depend on what coordinate system you're using to describe the vector with. Again, that should make sense because, yeah, the shadow that I'm projecting on the surface depends on the surface and the angle of my flashlight, but the length of the marker itself doesn't care. It's going to be what it is. So the fact that we can change our coordinate system and we have a quantity that doesn't change, namely the length, is a way of defining what's called a scalar. So before you may have defined a scalar as just a number. Here we're saying a scalar is something that is left what's called invariant, doesn't change if I change my coordinate system or change my basis. Okay, but what was this quantity? This is just v dot v. This is just the dot product of a vector with itself. So what that tells us is the dot product of a vector with itself gives us a scalar under the transformations we were considering. In reality, the dot product of any vectors will give you a scalar, but for this is something that's a bit more tangible. It's the length of the vector. So that's something to hold on to. We can show that something doesn't change depending on your coordinate system if we can express it as the dot product of a vector with itself, or the dot product of two vectors. So now that we've established that, we can move on to the relativity. All right, so to recap for vectors, we know how the components of the object in different coordinate system or in different bases are related if we have a certain transformation, like a rotation. That's how we know something is a vector. And for scalar, it shouldn't matter. It should be the same under all transformations, which is the same as an example would be like the dot product of two vectors. Now on to the special relativity. The way that we know if something is a vector or a scalar is exactly the same. The only thing that is different are the kinds of vectors and scalars that we work with and the transformations that we use. So instead of regular vectors with 3 components, we define something in special relativity called the 4 vector, because, well, you have one extra component because of time. So the 4 vector that is usually denoted with a Greek index as opposed to a Latin index. Latin goes from 1 to 3, x, y, and z, and we can have some v mu, where mu goes from 0, 1, 2, 3. So 1, 2, and 3 are still the spatial part. I'll call that r. And the 0 component is the time component. Okay? So for it to be a 4 vector, we have to know how its components transform under Lorentz transformations. They have to transform as vectors under Lorentz transformations. So that's to say, these two vectors in different reference frames are connected via the Lorentz transformation. Okay. It might be also useful to define, I have this with an upper index, and that's because it's actually different from something with a lower index. You can define the lower index as something called the metric tensor, g mu nu, acting on v nu. So the metric tensor, I'm going to erase this. It's not something that I really want to get into. I have plenty of resources that I'll probably link in the description if you're more curious. But the metric tensor, g mu nu, is 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. And these minus signs are going to play a big role in how we define the dot product of 4 vectors in just a second. It should shed some light. So let's go ahead and get into that. We have the special relativity version of the scalar. It's still a scalar, but we typically call it something else, namely a Lorentz invariant. Lorentz invariant. This is just because it's more suggestive on the type of transformations we're considering. Invariant, unchanged. This part means under Lorentz transformations. So in this, same thing applies. Lambda is equal to lambda prime. It didn't change. And as an example, we would have the dot product of two 4 vectors. So let's call it v mu dot v mu. So this is how we denote the dot product of 4 vectors, one with an upper index, one with a lower. And since we have this lower index here, all of the components of this upper index are going to be multiplied by a -1, the spatial parts will, which is why this would be v0 squared minus vx squared minus vy squared minus vz squared, which is also just equal to v0 squared minus v vector squared. So this is how you define the dot product of a 4 vector with itself. You get this relative minus sign because of how you define this lower index guy, and these minus signs in the metric are what give you that relative minus sign. Okay, I don't want to get into it much more than that. But that's all the pieces of the puzzle. Now we know how to define a Lorentz invariant. We know that if we have a dot product of a 4 vector, it is guaranteed to be a scalar. It doesn't change under Lorentz transformation. So the next step is to see what kind of object is the mass. I went ahead and plopped the definition of the dot product of 4 vectors up here for future reference. We're going to need a couple things from the toolbox for the rest of this video, the first of which is going to be the definition of the Lorentz transformation. We're actually going to need that later on in the video, but I'll write it first. So the Lorentz transformation is given by this capital lambda, which is equal to this matrix, which is, and I'll get to what all these things mean in just a bit, a gamma minus beta gamma 0, 0, minus beta gamma gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, throughout the rest of this video, we're going to be assuming natural units. Usually, gamma is equal to a 1 over, defined to be 1 over the square root of 1 minus v squared over c squared. So the velocity divided by the speed of light squared. We are using natural units, which is where c is equal to 1. So instead of v squared over c squared, we're going to just be writing 1 minus v squared. Similarly, beta is usually defined to be the ratio of v over c. And since c is 1, we're going to just be writing this as v. Okay, so let me go ahead. This is already up here. The next thing that we are going to need is Einstein's energy relation, which says that the square of the energy is equal to the square of the mass plus the square of the momentum vector. Okay? And now we have everything that we need for the rest of the video. The next thing is to define the 4 momentum. It's one of the most important 4 vectors in special relativity because it characterizes both the energy and the momentum of the system, and it transforms as a 4 vector. What more could you want? So the 4 momentum is denoted p mu, and we're going to express this as a column vector. So we have energy, and then there's also going to be a momentum contribution, which is a p vector. Okay? So this is just shorthand for this. E, px, py, pz. Okay? So the next thing that I want to do is I want to take the dot product of the 4 vector with itself. In a sense, we're going to be finding the length of the 4 momentum, so to speak. So p mu, based on this definition of the dot product of a 4 vector with itself, it's going to be the first component squared, the 0th component squared, which is just the energy squared, minus the vector squared, minus the momentum squared in this case, minus p vector squared. So whatever this is, whatever this difference is, it is a Lorentz invariant. It does not depend on your reference frame because, as we proved, a length of a vector is a scalar. Okay, so if we look at this equation here, Einstein's relation, if we subtract the momentum term over, we get that the mass squared is equal to E squared minus P vector squared. But that's exactly what the dot product of the forward momentum is with itself. It's just this quantity here. So this whole thing is equal to m squared. And this by construction means that m is an invariant quantity. It does not change. It does not depend on your reference frame, and equivalently, meaning it does not depend on your velocity. So this, it is invariant. So we had a huge primer of talking about what vectors were and what scalars were, but once that stuff was established, well, it only took like one line to show that the mass is an invariant quantity. So the question is, why do people say that it changes? Why do people say that mass changes depending on how fast you're moving? Well, this isn't an issue with physicists disagreeing with this being an invariant quantity. What it has to do with is an issue of how you define inertia. You see, in regular old classical Newtonian physics, inertia is the property of matter that characterizes how hard an object is to accelerate given a certain force. Now, in Newton's second law, this is given by F equals ma. So inertia, in a sense, is just equivalent to the mass. How hard an object is to accelerate depends on how massive it is. Okay, more formally, this can be written as F is equal to the time derivative of the momentum vector. And as we'll see in a little bit, this always holds, this doesn't. And once we start to play around with the relativity, we'll see that we need to make an adjustment to something. And I'll show you what I mean, but let's just go ahead and jump right into it. So what we're going to do is we're going to compare form momentum in different reference frames and see what happens. Something that should be pointed out is we were able to show that the mass is an invariant quantity by showing that it can be expressed as the dot product of a 4 vector with itself. Something that could be useful to make a video on in the future, let me know in the comment section if you'd like to see it, is proving that this in fact is a 4 vector, because under that assumption, m is definitely a scalar, but to prove that this is a 4 vector requires a bit of technical care that I didn't include in this video. So just let me know if you'd like to see a future video where I show that the form momentum is a 4 vector. But from assuming that it is, let's carry on. So let's go ahead and transform it into a different reference frame. So in a different reference frame, P prime, the primed frame, is related to the unprimed frame via a Lorentz transformation. Now, if we're considering transformations in, say, the x direction, then the y and the z directions should be left unchanged, which is why in this Lorentz transformation for the y and z components, we're just going to be multiplying everything by 1. So we're not going to write it out. It's just going to stay the same. But let's go ahead and write out the other two components, the time and the x components. So we have that the energy and p prime x, these are all primed, is equal to the Lorentz transformation p gamma minus beta gamma and gamma e px. If we do the matrix multiplication, this is just equal to gamma e excuse me, minus beta gamma px. This is not to be read as two different components of a matrix. This is the first component of a vector, okay? Then we have minus beta gamma e and gamma px plus gamma px. Let's go ahead and equate the components of the 4 vector. So we have e prime is equal to gamma e minus beta gamma px. P prime x is equal to minus beta gamma e plus gamma px. And as I said, the x or the y and z's are left unchanged, so we have p prime y is equal to py and p prime z is equal to pz. Okay, so this is how the components of the form momentum in one frame are related to the components in another frame via these relationships right here. In nuclear and particle physics, oftentimes in calculations, it's convenient to have the first frame be the rest frame and then do a Lorentz transformation to find out what these values should be in the actual lab frame where things are moving around in accelerators or something like that. So if we take the initial frame to be in the rest frame, so RF for rest frame. Well, in the rest frame, the momentum is 0. You're not moving relative to yourself. So we have that P is equal to 0. And if we look at Einstein's relation, if P is 0, then the energy is just equal to the mass. So we also have that E is equal to the mass. So let's see how this equation reduces or simplifies. We have E prime is equal to, this term is 0 because P is 0. We have gamma E, which is gamma M. Gamma times the mass. Now, when I first saw this, I found this very confusing because at first glance, if you haven't already shown and convinced yourself that the mass is an invariant quantity, this kind of looks like mass being transformed, right? Mass changing depending on your reference frame, but that's not what's changing, it's the energy, okay? So then we also have for P prime, this is going to be equal to, again, P is 0, so we have minus beta gamma E. Now beta is just the velocity in natural units. Beta is v over c, c is 1, so beta is the velocity. So this is minus v gamma, and E is the mass. We're rearranging this, just minus m. We can also, so the v is the relative velocity. We can have the relative velocity moving in the opposite direction, in which case v goes to minus v, and we get rid of this minus sign. Okay, so that's just going to be mv times gamma. This looks extremely similar to the regular momentum relationship that you know from regular classical Newtonian physics. So what people did is they defined a new type of mass. They said that mass is defined to be the coefficient that multiplies the velocity, relates velocity to the momentum. So let's define a relativistic mass that is defined to be m times gamma. Then what you have is that the momentum is equal to the relativistic mass times the velocity. So what this served is it was an attempt to say, no, mass is what characterizes inertia. The thing that resists acceleration is the mass. So if we find out that things depend on your reference frame, let's absorb all of that stuff and define a relativistic mass. And as a consequence, we also have something that looks more familiar to our students who are more used to classical physics because the form of the equation doesn't change. If the velocity is very, very low, then this is just the regular mass times the velocity. So non-relativistic velocities, you recover the old Newtonian definition of the momentum. The thing that makes this so confusing is you can't just tack this relativistic mass onto anything and think that your equations hold. For example, the force is the time derivative of the momentum. So can I just say that the force is equal to m relativistic times the acceleration? The answer is no, because what this is it's the time derivative of the relativistic mass times the velocity. So the relativistic mass was m gamma times the velocity. This is, as we've shown, this is an invariant mass, so this can be pulled out. This is m d over dt gamma v. But gamma is a function of velocity, and the velocity is a function of time. So you have to use product rule when you take this derivative. So this is equal to, so this means that f is equal to, running a bit out of space, m product rule. So we're going to have gamma dv dt, which is a, plus v dot v times gamma, v times d gamma dt. So if we could just treat this mrel as a mass, then F equals ma could just be substituted with mrel times the acceleration. But this guy m gamma is mrel times a. But we get this additional contribution, v dot, we can evaluate this derivative using chain rule, dv over dt, d gamma over dv, times the mass because it's distributed, which in general is not zero because you can't always assume that velocity is perpendicular to the acceleration. So this notion of a relativistic mass is extremely misleading because it's not a mass and it just can't be treated like one. But these people who insisted on using the terminology of relativistic masses 50 years ago, we now just call the total energy. And in the rest frame, yeah, the energy is just the mass and therefore is just the inertia, but in any other frame, there's going to be kinetic contributions. So why can't you travel faster than the speed of light? It's not because your mass increases, it's because your inertia does. And your inertia doesn't just depend on the mass, but it also depends on the momentum or the kinetic energy. And when you substitute saying mass depends on velocity with energy depends on velocity, well, that's almost obvious. But if you're a professor and you've been using this relativistic mass notation, I urge you to stop. Or if you insist on using it, then, just please make it painfully clear that it's not to be interpreted as an actual mass, because that confusion has just been propagating through the introductory physics textbooks throughout history. But I hope this helped clear up some confusion. I hope you guys enjoyed the video. Let me know in the comments section if you did, and I'll see you guys there.